So a pleasant day to each and everyone, most especially to our professor in EDD SE 705, Advanced Topics in Chemistry for Teachers, Dr. Philemon A. Pimentel Jr. By the way, I am Sir Fermin John Crispo Blanco, teaching at Vicente Andaya Senior National High School, Senior High School Department, and today I am tasked to discuss to you what is all about the chemical equilibrium. So in the chemical equilibrium are the following topics. First is the law of mass action, the equilibrium constant, the Le Chatelier principle, focusing on the effect of concentration, temperature, and pressure. Next is the free energy and equilibrium, the solubility product, common ion effect, pH and buffer solutions. Next is acid and bases, focusing on the concepts of Bronsted and Lewis, and lastly, the hydrolysis of the salts. Some reactions may proceed to completion, which relies upon the nature of reacting substances and the external conditions affecting such reactions. Reaction that forms precipitate, evolves gas, or produces a slightly ionized solution which may reach near completion since the formation of these products removes reacting ions from solution. So what does this chemical equilibrium really means? So of course it is a condition where the rate of reactant is equal to the rate of the product. So in this condition, the two opposing reactions may occur that points toward the formation of products, and the other, which is the products, recombined to form the reactants, or of course also known as the reversible reaction. So meaning the reverse reaction will start the rate in a forward reaction, then it will decrease until it will be on its optimum level, which of course means the chemical equilibrium. So reversible reaction is in a state of dynamic equilibrium, meaning it is progressing, and meaning that the two opposing rates are in progress. The time required for a chemical equilibrium to be established varies among different reaction systems. An example of that is the neutralization reaction, which is of course a rapid reaction. So reaction kinetics is a study of rates of chemical reaction and the factors that influence reaction speeds. So here is a clear illustration of chemical equilibrium. So beginning with a mixture of hydrogen and nitrogen gas, the rate of the reaction is initially rapid because the concentration is very high. So as the reaction proceeds, the concentration of the reactants decreases while the concentration of the product, which is ammonia, is increasing. So at the equilibrium, the rate of the depletion of nitrogen and hydrogen gas is equal to the rate of the formation of ammonia, and thus the rates of the forward and reverse reactions are equal. So the concentration of the various species is fixed at equilibrium because the product is being consumed and formed at the same rate. In other words, the reaction continues indefinitely, which is of course dynamic or progressing, but the concentration of the products and reactants is fixed in a equilibrium state, and this explains the equilibrium in a dynamic state. So let's proceed to the law of mass action. So it states that the rate of a chemical reaction is directly proportional to the product of the molar, which is the formal concentration of the reacting substances, is raised to the power indicated by the number of ions or molecules appearing in the balance equation. For a reaction, of course, the reactants is A and B will, of course, will result to a product. So according to mass law, the velocity is proportional to the product of molar concentration, which of course the velocity is directly proportional to the concentration of A and also the concentration of B. So in other words, if we will convert it proportionally to the equation, V is equal to the equilibrium constant of A times B. So if in the balance equation, M molecules of A react within molecules of N of B, so it will result to a certain product. So the overall expression of the velocity is written as V is equal to the equilibrium constant of A raised to M times B raised to N. So by raising the concentration of the species, it follows that if you double the reactant, the velocity will also be doubled. So K, which is the equilibrium constant, is 1, the A is the 2, and the B is 1. So V again is the equilibrium of A raised to 1 times B raised to 1. And of course, we will have the result of 2. So if the two reactants are also doubled, of course, we can have a product also of a double, which is in 4. Considering the previous hypothetical reaction to be reversible with designated product, which as you can see is the reactant and also the product, and the velocity of expression for the reaction are the following. So the V sub 1 is equal to the equilibrium constant of 1 with a reactant of A sub M times B sub N, which is of course in a forward process, and the V sub 2 is the equilibrium constant of 2, which is the C raised sub O times D sub P, which is in a reverse reaction. Since at chemical equilibrium, the two rates of the forward and reverse reaction are equal, and of course, as explained previously, these two velocities are equated. So of course, the V sub 1 is equals to the V sub 2. So substituting the formula of the velocity, which is the equilibrium constant 1, is of course the A sub M times B sub N is equal to the equilibrium constant 2, which is the C sub O times D sub B. So let's go now to the concept of chemical equilibrium. Of course, it is opposing reaction occurs at equal rates. It's a dynamic process, or it never stops, or it doesn't end. Next is the concentration of reactants and products are constant. The rates of forward and reverse reactions are equal, and equilibrium can be reached from either direction of our reactants or a product. So each reversible reaction has an equilibrium constant. So when the reaction reaches equilibrium, the equilibrium constant will not change. So the magnitude of equilibrium constant can be altered only by changing the temperature, and thus the equilibrium constant of temperature is dependent, and it is necessary to specify temperature for each equilibrium constant. An example of that is the industrial application, which is a chemical industry will choose a temperature that will maximize the yield of the desired product. So let's proceed to the principle of Le Chatelier. And of course, it states that when a stress is applied to a system in the equilibrium will shift in a such a manner as to relieve or neutralize the stress. So of course in our life we also have stress, stressors, but also if we will connect it into chemical equilibrium, there are a lot of stress also that is happening on it. So what are the stresses? These are the following that affect or influence chemical equilibrium, such as temperature, the pressure of gases, and the concentration. So we will be learning this one by one. So first is the effect of pressure change. So of course, the effect of pressures on solids, liquids, and gases are insignificant since they are not compressible. However, for gases, a slight change in pressure or volume is so significant because gases are free to expand and compress. If we will just take a look on this reaction, the mixture of the hydrogen and the nitrogen gases will result to nitrogen tetrahydride. And so in any change in volume or pressure is a stress to the system. If the pressure is increased using Le Chatelier principle, the stress can be relieved by shifting the direction of the equilibrium to the product side that favors a decrease in volume, and that is the formation of the 2 moles of ammonia. In summary, pressure affects equilibrium composition only of reactions that involve at least one gaseous substance. The relative number of moles of gaseous products and reactants must differ, meaning that the equilibrium will shift to increase the number of moles of gas when the pressure is increased. Next is the effect of temperature change. So threat temperature as reactant or product in the reaction. When the temperature is increased in an exothermic reaction, the equilibrium will shift to the reactant side. So meaning when the reaction is increased, also in an endothermic reaction, the shift of the equilibrium is towards the product side. Next is the effect of concentration change. So a change in the concentration in either in a reactant or a product shifts the equilibrium. So if the reaction is increased in the reactant side, the direction of the equilibrium will shift to the formation of a certain product. Meaning that if the concentration of the product is increased, the equilibrium will shift to the reactant side. So of course, a removal of the reactant or product also affects the chemical equilibrium. So let's go now to the effect of the catalyst. Of course, catalyst is a substance that alters, that speeds up the rate of the certain reaction. So of course, it alters the rate of the reaction without itself consumed in the entire reaction process. So of course, a catalyst has no effect on the direction of the equilibrium, since applying a certain catalyst to the reaction system means that both the rates of the product, or I mean in a forward and a backward reaction, are changed in the same extent. So let's go now to the free energy and equilibrium. So the equilibrium point occurs at the lowest value of free energy available to the reaction system. So the delta G is equal to 0 is equal to the delta G theta plus RT ln the equilibrium constant. Delta G theta is equal to the negative RT ln equilibrium constant. So here is the qualitative relationship between the change in standard free energy and the equilibrium constant for a given reaction. Of course, in the delta G, theta is equal to 0, while on the equilibrium constant is equal to 1. Delta G, theta is less than 0, while the equilibrium constant is greater to 1. Next is the delta G, theta, which is greater than 0, while the equilibrium constant is less than 1. So the maximum possible useful work obtainable from a process at a constant temperature and pressure is equal to the change in free energy. So here is the equation. The maximum work is equal to the delta G, which is or the free energy. So achieving the maximum work available from a spontaneous process can occur only via a hypothetical pathway. So any real pathway wastes, of course, energy. So all real processes are irreversible, meaning that you cannot turn it again. First law, which is, of course, you can't win. You can only break even. The second law is you can't break even, and as we use energy, we degrade its usefulness. So let's proceed now to the acid and bases. Of course, acid and bases, of course, have different and a distinct characters or the properties. So acids gives foods a tart or a sour taste. Aqueous solutions of acids are strong or weak electrolytes. Acids can cause certain dyes, called indicators, to change color, and many metals such as zinc and magnesium react with aqueous solutions of acid to produce hydrogen gas. Acid and bases also have distinct properties. One of the examples is the soap is a familiar material that has the properties of a base. So of course it is a bitter taste. Its general property of a certain base. The slippery feel of soap is another property of bases. So bases will cause an indicator to change its color. Bases also form aqueous solution that are strong or a weak electrolyte. Sodium carbonate and ammonia act as a basis when they form aqueous solution. So neither of these compounds is a hydroxide containing compound, so neither would be classified as a base by the Arrhenius definition. In 1923, the Danish chemist Johannes Bronsted and the English chemist Thomas Lowry were working independently. Each chemist proposed the same definitions of acids and bases. According to Bronsted-Lowry theory, an acid is a hydrogen ion donor and a base is a hydrogen ion acceptor. So this theory includes all the acids and bases that Arrhenius defined. It also includes some compounds that Arrhenius did not classify as bases. So you can use the Bronsted-Lowry theory to understand why ammonia is a base. So when ammonia dissolves in water, hydrogen ions are transferred from water to ammonia to form ammonium ions and hydroxide ions. Ammonia is a Bronsted-Lowry base because it accepts hydrogen ions. Water is a Bronsted-Lowry acid because it donates hydrogen ions. So let's go now to the conjugate acids and bases. When the temperature of an aqueous solution of ammonia is increased, ammonia gas is released. In the reverse reaction, ammonium ions donate hydrogen ions to hydroxide ions. The NH4, which is the ammonium, acts as a Bronsted-Lowry acid, and the OH, which is the hydroxide, which is the acceptor, acts as the Bronsted-Lowry base. In essence, the reversible reaction of ammonia and water has two acids and two bases. A conjugate acid is the ion or molecule formed when a base gains a hydrogen ion. So the ammonium is the conjugate acid of the base ammonia. So let's proceed to Lewis acids and bases. So how did Lewis define an acid and a base? So according to him, an acid accepts a pair of electrons and a base donates a pair of electrons during a reaction. So this definition is more general than those offered by Arrhenius or by Bronsted and Lowry. A Lewis acid is a substance that can accept a pair of electrons to form a covalent bond, while a Lewis base is a substance that can donate a pair of electrons to form a covalent bond. The Lewis definitions include all the Bronsted-Lowry acid and bases. Consider the reaction of hydrogen ion and the hydroxide ion, which is of course the hydrogen ion is a Bronsted-Lowry acid and the hydroxide ion is a Bronsted-Lowry base. So one of course is the donor, which is in a form of acid, and the other one is the acceptor, which is the base. So the proton there is a hydrogen ion. So the hydroxide ion can bond to the hydrogen ion because it has an unshared pair of electrons. The hydroxide ion is also a Lewis base, and the hydrogen ion, which accepts the pair of electrons, is a Lewis acid. A second example of reaction between a Lewis acid and a Lewis base is what happens when ammonia dissolves in water. So the hydrogen ions from the dissociation of water are the electron pair acceptor and the Lewis acid. Ammonia is the electron pair donor and the Lewis base. This table compares the definitions of acids and bases. So in the acid-base definition, it was categorized into three types. First is the Arrhenius, which is of course in the acid, the hydrogen ion is the producer, while on the base is the hydroxide ion is the producer. Bronsted-Lowry is the hydrogen ion is the donor in the acid, while the hydrogen ion in the base is the acceptor. And lastly, the Lewis, of course, that in the acid it is an electron pair acceptor, while on the base it's the electron pair donor. The Lewis definition is the broadest. It extends to compounds that the Bronsted-Lowry theory does not classify as acids and bases. So to identify the Lewis acids and the Lewis base in this reaction between ammonia and the boron trifluoride, of course, as you can see, the ammonium chloride and the boron trifluoride will have its product of a ammonium boron trifluoride. So let's analyze it one by one to identify the relevant concepts. When a Lewis acid reacts with a Lewis base, the base donates a pair of electrons and the acid accepts the donated pair. So to apply the concept to this problem, identify the reactant with the unshared pair of electrons and the reactant that can accept the pair of electrons. Of course, we need to draw dot structure to identify which reactant has an unshared pair of electrons. So as you can see, the ammonia has an unshared pair of electrons to be donated. So the boron atom, which is, of course, can accept the donated electrons. So to classify the reactants based on their behavior, Lewis bases donate a pair of electrons, so ammonia is the Lewis base. In the Lewis acids, accept a pair of electrons, so boron trifluoride is the Lewis acid. So let's go now in weak acid. Since it is an equilibrium, there is an equilibrium constant also related to it, called the acid dissociation constant. So as you can see on the table, it was said that the greater the value of the acid dissociation constant, the stronger the acid is. So let's go now to weak bases. One of the example of a base is ammonia in a form of NH3, and it is a weak base. Like weak acids, weak bases have an equilibrium constant called the base dissociation constant. In the equilibrium calculation, work the same as for acids using the base dissociations constant instead. Next is water. Water may be considered as a weak electrolyte because the purest water is able to conduct electricity to a measurable extent. Water acts as a solvent by entering into chemical combinations via H bonding or by donating or either accepting protons, which also acts as either an acid or a base. Water's ability to act as an acid or a base is amphoteric, meaning it is due to its ability to ionize by itself. The self-ionization of water is the chemical reaction in which the two water molecules, as you can see below, react to produce a hydronium ion and a hydroxide ion. So it is an example of autoprotolysis and relies on the amphoteric nature of water. So in a chemical equilibrium of water is temperature dependent. So the calculation of hydronium and hydroxide concentration of acids and bases in an aqueous solution is dependent. So let's go now to the potential hydrogen ion and the potential hydroxide ion. When we say pH, the measure of hydronium ion concentration, so it was said that the higher the pH, the less acidic is the solution. If we will just take a look on the pH scale, of course, the 7 is of course the pure water, the milk, the human saliva, and the blood. If we will just take a look deeply, of course, the higher the pH, the less acidic is the solution. 8 is the seawater, the eggs. 9 is the baking soda, phosphate, detergents. 10 is the borax and antacids. 11 is the milk of magnesia. 12 is ammonia and non-phosphate detergents. 13 is bleach. And lastly, 14, the sodium hydroxide. While on the other hand, 6 is bread, salmon, potatoes, normal, rain. 5 is the tomatoes, bananas, and coffee. 4 is the orange juice, acidic soil. And 3 is sodas, vinegar, lemons. 2 is battery acid and the normal stomach acid. 1 is the upset stomach acid, and 0 is the hydrochloric acid. So let's go now to the common ion effect. So of course it is the effect of increasing the concentration of one ion in a solution of a weak electrolyte in order to decrease another ion of the equilibrium mixture. The common ion effect follows the concept of the Le Chatelier's principle, which of course said that when a weak acid or weak base is added with its ions or salt, the equilibrium is upset and thereby shifting its direction as to relieve the stress. To what extent, thus, the concentration of each species is affected by ammonium ion? The reaction of a weak electrolyte with water produces relatively few ions in a certain solution. For instance, in acetic ions, only few particles of hydronium and acetate ions are present in the solution. As a consequence, a large increase in a acetate ion concentration produces a corresponding large decrease in hydronium ion concentration, but does not materially affect the total concentration of undissociated acetic acid. So this is a common ion effect. So let's understand buffer solutions. Buffers are solutions that resist a change in pH. They are made up of weak acid and its salt, or weak base and its salt. A special case of common ion effect, and also an addition of strong acid or base which do not change their pH much. Added H or a hydrogen ion reacts to completion with the weak base. Added of hydroxide ion reacts to completion with the weak acid. So one of the example is the interstitial fluid, which has a buffer system of bicarbonate for metabolic acids. The phosphate and protein, which is not important because concentration is too low. On the other hand, the blood, which has a buffer system of bicarbonate, which is important for metabolic acids. The hemoglobin, which is important for buffering of the carbon dioxide and the hydrogen. The plasma proteins is for minor buffer. The phosphate, which is the concentration too low. The intracellular fluid, which is a buffer system of proteins, which is important for buffer of extracellular hydrogen ion. The phosphates, which is important also for buffer. The urine, which is a buffer system of phosphate, which is responsible for the most of the tetratable acidity. The ammonia, which is important for the formation of the ammonium and hence excretion of the hydrogen ion. And lastly is the bone, which is the calcium carbonate, which is in prolonged metabolic acidosis. So let's go now to the hydrolysis of salt. The sodium acetate is the salt of a weak acid, which is the acetic acid, and the strong base, sodium hydroxide. The acetate ions will react with the water. So the acetate ion is a Bronsted-Lowry base, and any anion derived from a weak acid will be a weak base. So the ammonium chloride is the salt of a strong acid, which is the hydrochloric acid, and the weak base, ammonia. So the ammonium ions will react with water. The ammonium ion is a Bronsted-Lowry acid, and the solution will be acidic. Any cation derived from a weak base will be a weak acid. And lastly, salts form by reacting a weak acid with a weak base. So to determine whether a salt of a weak acid and a weak base will be either basic or acidic, it is necessary to compare the values of the acid dissociation constant and the basic or the base dissociation constant to determine the relative strength. So if the acid dissociation constant will be greater to the base dissociation constant, salt will be acidic. So if the acid dissociation constant will be less than the base dissociation constant, salt will be basic. One of the example is the ammonium fluoride. So of course, the acid dissociation constant of the ammonium is equal to 5.6 times 10 raised to negative 10, while the base dissociation constant of fluoride is equal to 1.4 times 10 raised to negative 11, we can have the solution of, or the solution has the pH of 6.2. I hope that you learned something in my discussion. Thank you and God bless us all.